This is lecture 12 in introductory class in electricity and magnetism. And in this lecture, we're going to talk about, or I'm going to talk about, energy, so electrical energy, but as well as kinetic energy. And I'm also going to describe and define for you the electric potential, which is given the symbol capital V. So there's a couple of learning outcomes. So these are the things that this lecture is supposed to help you become able to do. So first one is calculate work and potential energy for distributions of electric charge. We're going to imagine having some charges around and wondering about energy associated with that, and also about what's involved in making changes. That's called work. And then calculate the potential. So you notice that the word energy is not here. So let me drive this point home a little bit. Not potential energy, right? That's kind of strange. It's the potential. This thing called V, for a distribution of point charges. So again, you're going to imagine some electric charges sprinkled around in space, and we're going to calculate this thing called V for it, the electric potential. And then we're going to see that there's actually a relationship between work and potential. There's definitely a relationship between work and potential energy up here. This is a story I'm sure you're aware of. And then down here, though, I'm going to show you the relationship between thinking in terms of the electric potential, not energy, and the idea of work. So in order to do these things, I have these three sections. And honestly, they're going to sort of blend together as I talk through my little lecture on a piece of paper, or a few pieces of paper. At some point, we're going to, so we'll start off by talking about potential energy. So we're not talking about V in this case, we're talking about potential energy, or sometimes the symbol is U for potential energy, and this is what I'm going to use as a symbol. And we're going to imagine this in the most basic, simple way. We're going to imagine pushing or pulling 2 point charges together. And we're going to talk about work being done by external forces and the total energy of a system. And if we want to talk about total energy, one of the types of energies that we need to address is called the kinetic energy. And I'm going to describe a way that we can not worry about kinetic energy. And then also, I think this is instructive in just a basic physics kind of a way, and not necessarily so much for the current topic, but the difference between internal forces and external forces with respect to work being done. Of course, both of them do work, but it's the external work that we're going to concern ourselves with in this lecture. So after that, we'll define this function. You'll notice that it is a scalar function. That is, there is no little vector symbol above the capital V. So it's a scalar, physical scalar function of space. So these are, the XYZ coordinates of space. So we'll imagine a point charge, and we'll talk about the potential of that point charge, the electric potential. I may bring up some thoughts about energy. Not energy, the units and the dimensions. SI unit of energy is the joule, but the SI unit of this function called V is the volt. So this is the beginning of thinking about this idea of voltage. So also, we'll be talking about the potential energy of a charge distribution, like a charge distro, like a charged rod or a charged shell or an assemblage of point charges is in fact what I'm going to talk about in this lecture. So there's, on the one hand, talking about the potential energy of a distribution of point charges, but then on the other hand, there is the potential of a distribution of point charges. So there's two ideas here, and here is a way to think about the difference between them. I'll let you read that on your own. All right. So let's start with a thought experiment, and we're going to use this thought experiment to think about energy at first. And so I'm talking about, for example, thinking in terms of units of joules. Okay, so here's our thought experiment. Let's imagine that I have some initial sort of state, at some moment in time, early moment in time, and I have two charges, a pair of charges. So one of the charges has value charge Q sub A, and the other charge has value Q sub B, right? They could both be positive or both be negative, or one is positive, one's negative. Lots of combinations of things. But let's say that initially they're sort of far apart. So we could say that we have a distance between A and B with some initial separation. So the I is for the initial state, and this is the separation distance between them, some number of meters or centimeters or miles, doesn't matter. So the thought experiment, this is interesting in and of itself, I guess. I mean, you could start to wonder, well, if they have like signs, then they're going to have an interaction that's repulsive. So plus plus will repel and minus minus will repel. Alternatively, they might have opposite signs, in which case at this separation distance they'll attract each other. So what? The interesting thing about thinking about energy is how you might take this system of two charges that are repelling or attracting each other and causing it to change from some initial state given by the separation distance, to some final state. Right? And let's say that the final state is such that the charges A and B are just simply close to each other, or closer to each other. So here is the final separation distance between these two charges. Right? So initial state and final state. In the initial state, we could have had a kinetic energy of charge A initial and a kinetic energy of charge B initial. And in the final state, there is also the case of kinetic energy A having some final value and the kinetic energy of B having some final value. So we can talk about kinetic energies. But just like in gravity, there is a potential energy. And the potential energy in electrostatics is actually the very same idea as in gravity. Except for whereas gravity is strictly only attractive, so you write down potential energies for only attractive interactions. In the case of electrical forces, right, electric potential energy, the potential energy function needs to be written down for repulsion as well as attraction, right? So, yeah. Okay, so it turns out that this is a useful definition of potential energy. So let me just tell it to you. So the way that the potential energy function gets written down for two charges, I'm just going to say that 2 point charges, so I should have said point, 2 point charges, let's say Q1 and Q2, are separated by distance r1, 2, right? So this is just the distance between 1 and 2. Just like up here, that's the initial distance between A and B. And this definition of the potential energy is going to be written this way. So the potential energy is equal to, it's the product of Q1 and Q2 divided by 4 pi epsilon naught R1, 2, and that's multiplied on the bottom. But R1, 2, remember, is only strictly a positive number. I mean, you could consider putting the equal sign there too, but that just means that Q1 and Q2 are directly on top of each other. And if you divide by 0, then what you're going to get is an infinite energy. So it tends to be just written as R1, 2 is just bigger than 0. Okay, so, and another thing is, I'm going to draw it explicitly, but there is an implicit positive symbol out here. So I'm just, yeah, so maybe I'll just leave it alone. But notice there's no symbol. In gravity, I'd like to remind you that the potential energy that you likely would have defined for gravity had a minus sign. It was G, say, M over R, like this. So G is the universal gravitational constant. Over here, the universal electrostatics constant is 1 over 4 pi epsilon naught instead. And there is a minus sign here, and that minus sign is because masses are positive, right? These are positive masses. There's no such thing as negative mass. And it's attractive only. So this is how we describe energies growing when the two masses are further separated. Over here, though, because we can have attraction or repulsion, it ends up making the it ends up being correct to just keep a plus sign right there, not a minus sign. But anyways, this is a definition for the potential energy. So if I wanted to include potential energy in this thought experiment, here is one way we can do it. And so let me put this potential energy up here. So we could say that there is a potential energy that really depends only on the separation distance. So I've got in this pairing, right? This is a pair of particles. There's 2 of them. Each particle could have motion energy, kinetic energy, but the potential energy is in the pair. It's in both of them being present. And then down here, the potential energy would be the potential energy associated with a different distribution of the charges, right? So here the charges are distributed far apart, and now here the charges are distributed close to each other. A larger charge density, you might say. There's more charges per volume of space. Up here, it's like 1/3 the charge density or something like that. Okay, so I have what's referred to as a pairwise potential energy, right? And the way you calculate potential energy is you look at the pair of particles and you ask how far apart are they. The product of the charges divided by 4 pi epsilon naught times the distance of separation is the potential energy. And if you go and you look at the dimensions of everything, this is dimensions of energy. And the SI unit of energy is the joule. Right, so that's how that calculation would go. Okay, so what I want to do, actually, let me also say, if Q1 and Q2 are like sign, then the potential is only ever positive. I wonder if you can see this in your mind. Like, so if Q1 and Q2 are like sign, that means it can be plus plus or minus minus, right? That's it. So if it's plus plus, then I've got a positive times a positive divided by a bunch of positive stuff, and U is positive. If they're both negative, then I have a negative times a negative on top, which is overall positive, divided by a bunch of positive stuff. U is still positive. If Q1 and Q2 are opposite sign, that means, say, Q1 is positive, Q2 is negative, or Q1 is negative and Q2 is positive, then the potential energy will be less than 0, right? This is the case, right? Plus and minus plus. This is when you get an attractive interaction, just like gravity. And in this attractive interaction, gravity needed to have potential energies that were less than 0. So this is how we match gravity. Gravity is an attractive interaction, and electrostatics is attractive if the charges have opposite sign. And when they have opposite sign, the overall sign of the potential energy, is negative. What's cool is electrostatics also gives us a way to have positive potential energies. That's very different from gravity. Gravity doesn't have this. All right, so let me move on and describe a little bit of backstory and thinking about where does the potential energy come from. So let's put this potential energy function, this is say the difference between two charges called A and B. So this is, I showed you that it's QA times QB divided by 4 pi epsilon naught distance between A and B. So that's R sub AB. Okay, so we've got this in our mind. So this is the backstory to this potential energy function. So here's the idea. So this is a potential energy function. And potential energy functions are only for what are called conservative forces. Coulomb's law is conservative. And when you have a conservative force, that is synonymous with being able to design an energy that, or a potential energy associated with that interaction. So let me tell you some more backstory, and it is based upon thinking about this this thing I described over here, where I have two charges pretty far apart, and then I do something or cause something to happen such that they are closer to each other, right? So let me think about this. I'll just redraw it here. So I've got two charges. This is say Q. Oh, this was QB, and here is QA. Okay, so QA and QB are the only two objects in my system of my thought experiment, right? So in my thought experiment, there may be a red pen and a piece of paper also close by, but I don't want to think about these two things as part of my system. I'm going to consider these two things external to my system. So I'm going to keep them not in the list of objects in the system. QA and QB interact with internal forces, right? These are internal because they are between objects within the same system. So these forces are internal to this system that I'm describing. Let me describe some external forces. I'm going to consider two people. There is person A and there is person B. And these two people are going to be responsible for doing external things to my system. What I'm going to ask person A to do, person A is going to stand here and exert an external force on a particle within the system I'm talking about, and person A is external to the system because it is not one of the objects mentioned in the system list, and this will be an external force on charge A. And person B will be also an external forcing agent to apply external force on charge B. Person A has a directive. So the external force on charge A is whatever it needs to be so that QA is always at rest. If QA is always at rest, then we can say that the kinetic energy of A is always zero, just doesn't change, right? If it doesn't change, then we'd say that the kinetic energy of A in the final case is equal to the kinetic energy of A in the initial case, and both of those are just zero. So that's what the job of the external force on charge A is. The directive for person B is to do whatever is needed so that this one is a little bit tougher to maybe swallow. Whatever is needed so that the kinetic energy of B in the final case is simply always equal to the kinetic energy of B in the initial case. So this means, this is the same thing as saying that the change in the kinetic energy is equal to zero for object B. Right? That's the job of the external force on QB. And so this is the initial, and so the final is the case of person A is still standing at the very same place holding charge QA, but charge QB is closer. Right, so this is person A doing its job, and here's person B doing its job. Okay, so this is the final situation. So initial to final. Okay, so conservation of energy What it does not say is that the energy of a system cannot change. What it does say is that the energy of a system is going to change if some external agents manage to do work, right? So this is the change in the total energy of my system, and my system is just the two electric charges. There can be external agents that can do work such that the energy of this system can change. Over here, these are directives on what the forces, the external forces, are going to do, right? They're really smart, and they're very strong, and they can figure out how to cause these forces to happen, right? And figure out how to do whatever is needed to fulfill their obligation or directive. And they are going to be able to possibly do this external work to cause this system of charges energy to change, right? But you have to remember how work is done. So the work done by external forces, it's equal to this. It's the integral, or actually, let me take away this designation for a second. It is the integral of a force. So this is the work done by a force, dotted along some path from some initial place to some final place, right? And so the work done by external agent A is the force by external agent A as it applies this force on a charge that does not move. So the work done by external agent A is 0. But the work done by external agent B, right? This person here, sorry, I'm mixing up uppercase and lowercase. External agent B, it's equal to the integral of the force applied by external agent B over a path that takes the particle B from here to here instead, right? It's so external agent B is going to push charge B inward, for example. All right, so F external B is a vector, and what's interesting about this vector is it's really hard to know what it's got to be. But let me tell you what it's got to be. It's got to be whatever is needed so that our kinetic energy is the same in the final state as it is in the initial state. One of the ways that we can cause this to happen is simply to say that the kinetic energy is not going to change, right? So d by dt of the kinetic energy, this is the time derivative, it's the time rate of change of the kinetic energy. Why don't we just say that it doesn't change ever? That is, whatever kinetic energy it has at the beginning, it has the same amount at the end. And the way we can cause that to happen is if the external force by B exactly matches the opposite of the internal force on B by charge A. This case right here, this is the situation of the net force on charge B right here equals to 0. These are the two forces that act on B. The little person pushes or pulls on B, as well as the charge A might push or pull on B just because of electrostatic Coulomb interaction. So I've got a Coulomb interaction that's internal,
and I've got an external force. And those two forces are forces on B. And if I make them be the same except for with an opposite sign, then the net force on B is 0. What that means is that the acceleration of charge B is 0. And if the acceleration is 0, then the kinetic energy can't change. So this is a way to do this. So in this case, if I choose the external force by B, this is what is needed. Just make the external force by person B exactly match the opposite of the Coulomb interaction between the two electric charges. So that's what's needed. So if I do that here, you can see that what I am going to imagine is putting this force, but with a minus sign, right, into this integral to calculate the work. So the external work is this business here. It's how the system's energy is going to change. And the way the system's energy is going to change, well, I've given these little people directives to not allow either kinetic energy to change. So the way that the energy can change is not because the kinetic energy changes, it's because the potential energy changes. And so what we get is a change in potential energy if our external agents agree not to change the kinetic energy. And so here is what physics gives us. So this is the physics of Newton's second law. It's the physics of energy conservation. So this is very deeply physical. But what I'd like to point out is the following thing. I have given you a way to calculate the potential energy at the final state as well as the potential energy at the initial state with this function here. But I'd like to show you that this actually has something arbitrary associated with it. So let me copy this statement. So the external work in my little thought experiment only results in a change in this thing called the potential energy. And I have a potential energy function which is only dependent upon the separation between the two charges, RAB. It's equal to QA times QB divided by 4 pi epsilon naught RAB, right? Let me try an alternate definition of this potential energy. It's an arbitrary alternate, right? So I'm going to make an arbitrary change. The arbitrary change is I'm going to say that it basically looks the same. It's still QA times QB over 4 pi epsilon naught RAB, but it's got plus 22,000 joules, right? So this alternate version of the energy is the same as the one I showed you in the beginning of this lecture video, but it is always different by the same amount. And honestly, I just randomly chose that just now. It's got no physical relevance that I can figure out to assign. So 22,000 joules, what the hell does that mean? It is simply arbitrary. So the reason this is interesting is because of the following. If I look at UF and UI, so if I calculate it with this, then it will be QAB, it'll be QA times QB divided by 4 pi epsilon naught. And then what I'm going to do is have, in the final case, a 1 over RAB final minus 1 over RAB initial. right? That's if I use this formula. But what if I use this formula? What I'll get is the external work required is equal to, I'll need to write it out more, so I've got to do U final. So if I plug in, that just uses the final value of the separation distance. So it'll be QA times QB over 4 pi epsilon naught RAB final, all that. But I've got this weird 22,000 joules, right? So that is, with this alternate definition of the potential energy, this is UF, and I've got to subtract off UI. So UI is QA, QB, 4 pi epsilon naught, RAB initial. And when I calculate for the initial separation distance, I still have to add on this arbitrary 22 kilojoules. And so what you can see is that with this arbitrary constant, right? So the thing is it's got to be a constant. It can't also depend on space. So it's got to be a constant. So with this arbitrary chosen constant, what happens with this minus sign is the arbitrary constant always cancels. So the thing I'm trying to show is this is physical, that the change in potential energy matches the external work in this particular thought experiment, with all the caveats about what happens to kinetic energy. So this is the physical conclusion. But I'm telling you that designing a potential energy that looks like this, so QA, QB, 4 pi epsilon naught R, this choice is up to an arbitrary constant, right? So that is, this is not strictly physical. What is physical about this is actually the dependence on the charges and the R. So it's sort of the functional dependence. It's not the zero, which is what the arbitrary constant is. This arbitrary constant, freedom, it comes from integration. You know, when you do an integral, right? If you integrate f, so if you integrate df by dx through dx without bounds, then this is always, it's the fundamental theorem of calculus. It's f of x, the indefinite integration of df by dx, but plus an arbitrary constant. This is the problem. So potential energy is not defined exactly by this process. This process only ever defines differences in potential energy. This is the physical conclusion is a physical statement about, so the only thing you can know is about changes. You can't know the value itself. The value itself, it's got a functional dependence that's very important, but it's also got an arbitrary origin or an arbitrary zero value, which is not important. Yes, so there's probably better ways to say that. So the next topic I want to describe in this lecture is how to calculate the potential energy stored up in a charge distribution. So the way you think about this is you imagine putting the charge distribution together, and the way you start putting together a charge distribution is you start with empty space. You start with an empty slate. So in the empty space, I'm going to migrate in a first charge. So there's Q1. So Q1's interesting. So now all of a sudden my space is not empty, but what I did was let's say with an external force of some sort, I went really far away and I grabbed a charge from really far away from the empty space, and I bring this charge up and I place it there. So what's interesting to say about that is, as I'm bringing this charge in, I am not fighting with, and I'm also not getting any help from any other electric charge, because there isn't any other electric charge. So the first one is free. So Q1 shows up and I didn't have to do any work to do it. So now I have a space with one charge. And if I want to bring another charge in, I imagine bringing it also in from very far away in a completely different direction. So I wander Q2 and I put Q2 here, for example. Right? So there is energy because I have two charges that are somewhat close to each other. And this energy is equal to, so this is the energy because 1 and 2 have a potential energy interaction. They have a force interaction. And this is equal to Q1 times Q2 over 4 pi epsilon naught, the distance between 1 and 2. But now I wander in a third charge, right? I'm building up a charge distribution. I'll wander in this third charge and I'll stick it here. So the thing about Q3 is I had to bring Q3 in, say, against Q1, but I also had to bring in Q3 against Q2 separately. And Q1 and Q2 act on Q3 independent of each other. So what I'm saying here is, in order to bring in, so this is energy that, this is work actually that I needed to do in order to bring Q2 in against Q1. But Q3, to bring Q3 in, I need to cause 3 to fight with 1. But I also need to pay the price of bringing 3 in against 2. So U is pairwise. So this potential energy function is pairwise. That is, I have to pick pairs of particles. And in 3 particles, I have 1, 2, 3 pairings. So I have to put in 3 potential energy functions. So the total potential energy for this system of 3 charges, right? The total potential energy of the system is equal to the potential energy because 1 and 2 are interacting, plus the potential energy between 1 and 3's interaction, plus the potential energy between 2 and 3's interaction. And so this is how you would add up the total potential energy of a system. Yeah, so that this is, so you can imagine other distributions. You could imagine a charged rod. And so let's say that what I want to do is take a charged rod that is of some initial length, L sub I, and I could imagine bringing in other little charges to stick on like this from infinity. And from infinity, it doesn't really matter which way you bring them in from. You could, if you were actually going to do this problem, maybe you would just bring him in from within the direction of the rod to make the rod longer and have some final length, for example. You could imagine, you can imagine any number of things. But the point is whenever you have a net charge localized, right? A localized net charge costs energy. Yeah. And also, it costs energy to change charge distributions. Like if you want to take a rod and bend it around or something like that, that's going to cost energy, because if the rod is all positively charged, you are going to cause this positive charge over here and this positive charge to become closer to each other, for example. Yeah, so you will need to input work energy in order to change the charge distribution in certain ways. In certain other ways, you'll get an output of energy, right? Like if you had a charged rod, but it was bent around into a circle like this, and then you cut this charged rod, it may snap open, right? And then if it's got inertia, it'll snap open and maybe wiggle or something like that, right? So there's definitely oscillators, and there's inertia. There's all kinds of interesting things going on. Yeah, so in fact, actually, this energy that I'm talking about here is the energy of chemistry. If you have an exothermic reaction or an endothermic reaction, those thermal things are, so that thermal energy is associated with electric charge being getting further from each other or getting closer to each other. Kinda. I mean, yeah, this is part of the story. So to finish out this video, I need to talk about electric potential. And I've told you earlier that this is a scalar, potential, and has a symbol capital V, which is a function of space, right? So this is like just like you can have a function, say f of x, that's a function of a one-dimensional space. This is a function of three-dimensional space. Okay. So I'm going to get there, but before I get there, let me tell you about some stuff that you already know about, and hopefully you learn from that anyways. So electric force, this is given to us by Coulomb's law. Coulomb's law. I'm sorry, I'm being sloppy, but so Coulomb's law is a pairwise law. It's the pairwise, force interaction forces between two electric charges with some separation distance. This gives rise to a vector, right? A force vector. And if you plug in some SI units to calculate the force vector, it's going to come back with units, say, of newtons, for example. It's a vector thing, or a vector idea, and the vectors you could say are, for example, it's the force on charge number 2 because of charge number 1. You can also talk about the force on charge number 1 by charge number 2, and these are Newton's third law pair, action-reaction, for example. And just because, how about the force on 2 by 3 instead? Right, so lots of forces. In fact, every pair has 2 different forces. So in the interaction between these 2 charges, there are 2 forces. There's a force on the first charge, and there's a force on the second charge. In the interaction between these 2, there's a force on the second charge and a force on the third charge, and then in the interaction there, there's 2 forces there too. Okay, so in this case, the force on 2, there is a net force on charge number 2. There's a force by number 1 on 2, and there's a force by number 3 on 2, right? So, yeah, no big deal. Electric potential energy is a really similar idea. It's also pairwise. There is a potential energy because 1 and 2 are close to each other. There's a potential energy because 2 and 3 are close to each other, etc. And when you go and you calculate the energies, you're going to get some number of joules. So there's some number of joules because of this distribution of charge. Yeah, back here, there's some number of newtons on that charge because of the others. All right. So you might wonder, what is this empty quadrant for? It's to talk about electric field. So the electric field, in this case, there are lots of ways to talk about it. But I'm going to talk about it in a way such that it's useful when I talk about this new idea called the potential. So the electric field. So let me draw these same three charges. Oops, I kind of drew them in different places, but here is Q1, Q2, Q3, and I'm going to put them down in a little circle, just to sort of group them together. And the idea of the electric field is everywhere out in the space around. So if I imagine there is a coordinate system, so X, Y, Z, so coordinate system, there are places in space out in, and even within, like in amongst the charges too, but this is easier to draw this way. So imagine a point out here with coordinate x, y, z, and I showed you a way to use the superposition principle to calculate what is the net electric field at P. But we need to designate whose electric field is this. This is the electric field at P due to, in this case, Q1, Q2, and Q3 together. So we can talk about the electric field vector there. That might be P1, which has coordinates x1, y1, z1. And here's another place, P2, whose coordinates are x2, y2, z2, for example, right? So I have places in space. And that's the sense in which this vector-valued function is a field. It's got a value at all the places P. Even places P in here. Like it could be that there's a P3, right? The point is this charge distribution does something to the space. It fills the space with what we were referring to as electric field. It's the electric field of those charges. Now, it is absolutely true that electric field is up in here, and we can talk about these forces in terms of an electric field, but these forces aren't associated with this electric field. For example, the force on charge 2 is associated with the net electric field of 1 and 3 by themselves, or together, but not the electric field of 2. Down here, the net electric field is due to all 3. Up here, if I want to understand what's the force on number 2, then I think about the electric field of 1 and the electric field of 3 combining with the superposition principle, right? Or I think about the forces on 3. So 3 feels the field of 2 and the field of 1 in a superposition way, for example. So this is the idea of electric field. Electric field is not actually in newtons, though. It's in newtons per Coulomb, right? Newtons per Coulomb. It's the sort of, it's the force per charge, and it's also a vector, right? So it's got some things in common with just force, but it's actually kind of like its own idea. And the electric field idea of a distribution of charge, when you go out into the space, you imagine using test charges, right? And you can get a field line diagram and things like that. Now the electric potential is kind of like the analogous move. So up here, we have newtons up to joules. Down here, I have newtons per Coulomb. The scalar potential is going to be units of joules per Coulomb in terms of units. So it's the same idea. Imagine Q1, Q2, and Q3. And I sort of imagine bundling them up and thinking about the space out here. And associated with this electric field, there is another way to think about the electric field. In fact, what you're thinking about is the integral of the electric field along paths between places. So there's a place, say P1, with coordinate x1, y1, z1, for example, and a place P2, whose coordinates are x2, y2, z2. So I've got these two places in space. And you can write down a function that is a function of coordinate. So you can talk about the potential at P1, and you can also talk about the potential at P2. And this potential function is based on a separation distance, r, and a generic charge, capital Q. But I need to show you how to use this. I'm saying some stuff that's kind of weird. So divided by r. So this is the useful potential function, and the units that it will work out will be units of energy per charge, right? So this is the potential function. Okay. So I want to tell you about a superposition principle for the potential. So I've got the sort of same little charge distribution. Let me circle it. So this little distribution of charges, and I want to study the potential of this charge distribution. This charge distribution has a scalar potential field out in the space around it, and this is a place in space, and this is another place in space. It looks like P2 is a little bit closer to the three charges than P1 is. So I want to describe how you can calculate the net potential V. So you could say this is net potential V. You could embellish this due to Q1, Q2, and Q3. This net potential is going to be written this way. It's the potential due to Q1, so it's Q1 over 4 pi epsilon naught times the distance between Q1 and, for example, P1. So it's the distance between these two. It's the location of Q1 and the location of this place. So R1, P1, plus, it is a superposition principle. So you add on what you get if you take Q2 divided by 4 pi epsilon naught R2 P1, right? So this is the distance between charge number 2 and the place P1, plus what you get if you do Q3 divided by, same stuff, 4 pi epsilon naught, the distance between the location of charge 3 and the position P1. So this is the net potential due to the three charges at P1. This is the potential value here, right? So I might put it's the value at P1, and the potential at the place P2 associated with the very same set of charges in the same place. Everything's the same, so in fact you can see that 4 pi epsilon naught on the bottom is a common factor. So it's Q1 divided by the distance between charge number 1 and position number 2 plus Q2 over the distance between charge number 2 and position number 2, and Q3 over R3P, P2, excuse me, right? So that's the voltage, or I mean, that's the potential at the place P2. So here's so this is describing the net potential at two different places. what you need to know is the values of the distances. So if you had a coordinate system, you would likely have to use some Pythagorean theorem stuff. So like, yeah, so, okay. So we can talk about a change in potential. So delta V from, say, P1 going to P2, this is equal to, so P2 is where you end up. So you like imagine some way to think about the difference between 1 and 2, where 2 is the end and number 1 is the beginning, right? Beginning to end. This is the potential at P2 minus the potential at P1, right? In this order, where the beginning, you start at P1 and you get to P2. And that's how you calculate the difference. This is the difference in the potential. If you think about what this is, it's got dimensions of energy per charge, right? This equation is energy per charge. So if I take this equation and multiply by some charge Q, so Q times delta V from P1 to P2, this is equal to Q times V at P2 minus Q times V at P1. What this is actually is the change in potential energy. It's the potential energy between, let me backtrack a little bit. I was going to say something that's a little complicated to explain. Let me explain it this way. So the work required by an external force to move charge Q from place 1 to place 2 is equal to Q times the electric potential, the scalar potential at P2 minus the potential at P1, right? Or Q times delta V, P1 to P2. So this is the way you can calculate what is required of an external force to do this. So if you can calculate the potential at this place and then calculate the potential of that place, these are two separate energy per charges. And if you want to move a charge little q from P1 to P2, then the work involved by, the work required by some external person in order to push Q from place 1 over to place 2, the work required is simply Q times the difference between the potentials at the two places. If you wanted to talk about the work directly, right, that work would be the force by some external agent dotted with displacements starting at place 1 and ending at place 2. That's another way to calculate this very same work. This is difficult. This is a difficult way. This right here is easy because it's easy to calculate the potential at different places, and it's easy to calculate the difference in the potential between two places. And then once you have that, you just multiply by the charge that you're moving. Yeah, simple.